Okay, hello everyone. Morning, afternoon, and evening for everyone who's on the line. I'm going to go ahead and start sharing my presentation, which today is what we learned moving hundreds of servers into the cloud. So I'm with Expedia, and this is from one of the brands in Expedia, hotels.com. We were moving hundreds of our services into the cloud, and we learned quite a bit doing that. So let me just move on to the next slide here. And this is the agenda. This is the talk is divided into 5 sections. We found out certain particular things that are very useful about JVM metrics that you want to be able to monitor, and JVM configurations that were really useful to know. We also found out a lot of things about using NoSQL, and I'm actually going to explain why that's quite so popular. NoSQL is popular, why people are choosing Cassandra and DynamoDB, and then how to use them in the best way. And then I'll go into Kubernetes, and there's a couple of different sections there. One is all the basic resource utilization and how best to set those, and then going on to Kubernetes scaling, which is really a hot topic at the moment, and what we learned about scaling. So just the pictures here, as you can see, I work for Expedia, so they're all holiday themed pictures. Yeah, hopefully everybody's going to be able to go on holiday in 2021. It's been a hard 2020. Okay, so let me go into the JVM metrics. And the main thing that you want to do is obviously to expose the metrics in some way. And it's fairly standard. Anybody using a JVM would expose them using mbeans. You can expose them other ways, but this is really the easiest, simplest mechanism because there's quite a lot of support in the industry. Like, for example, Dropwizard and Micrometer will expose them straight away for you in a very nice way. They are exposed from your JVM on a particular port quite often. So if you're going to do that, you make sure that that port is not exposed to the world and only internally exposed. So we did involve our security team to review how we were doing that, to make sure that only internal access was available to those and not external access. Obviously, you don't really, I mean, it's not terrible if your metrics are exposed, but JMX can make available other things than metrics that are terrible to be exposed. So you don't want to expose your JMX mbeans externally from your organization. The way we did it initially, we use Graphite, which is a common time series databases along with that Grafana uses. So if you haven't heard of them, Grafana is a way of visualizing. It lets you create graphs of any kind of metrics, and it's very common within our industry, fairly standard. A lot of systems use Grafana, but Grafana doesn't hold the data. It reads the data from a time series database. Graphite is quite a common mechanism. So with Graphite, what happens is that your metrics are pushed by the JVM into Graphite, and then Grafana will read those and display them in charts. What we found was that Graphite had scaling problems when you're scaling to large numbers. They're not problems that you can't overcome, but the industry as a whole tends to be moving to using Prometheus as the time series database, because you get that with Kubernetes, and so people just naturally, since you've already got that embedded, people tend to be moving towards that. And there's a difference in that Prometheus is a pull time series database. Graphite is push. So push is the JVM pushes it. It actually makes a request to Graphite with the data. Prometheus is pull in that it actually connects to the JVM on the standard port, pulls the metrics in at its own pace. So there's a slight difference there, and there's pros and cons to push and pull, but industry as a whole is moving towards Pull, and Prometheus. So the kind of metrics that you should be doing, the JVM metrics, all of these, the class loading, compilation, and so on, I'll go through them in a little bit more detail. Over on the right is just a JConsole picture. If you use JConsole, you can access all of these metrics quite straightforwardly. And going into these in a little bit more detail, the JVM memory and memory pools are really useful to know, to be able to monitor. So this isn't specifically for the garbage collection. There's another little frame I have for the garbage collection, but things like the code cache, the meta space, the compressed class space, and the non-heap memory. These are all things that if you have a problem and it's in one of these areas, you'll be very, very grateful that you've got the metrics exposed. So bear in mind that what I'm talking about here is if you have a problem with your application and you're investigating it, these are the kind of metrics that you want to be able to go into and see what happened over the JVM lifetime. And that's why these metrics are very useful. Similarly, threads and threading, very useful. I don't often see applications with deadlocks nowadays, but when you do, it's very useful to have it monitored, as well as how many threads are runnable and so on. These are all very useful to see when you're investigating a problem. The garbage collector metrics are really important. A lot of the applications tend to have garbage collection, I wouldn't say problems, but they're not non-optimal configurations for garbage collectors. I'll talk about that in a little bit more detail later. But one of the things is that we, as an organization, did an investigation into several hundred of our incidents. And one of the things we did was we categorized them as to not what caused the incident, but what could resolve the incident. And of the ones where the JVM configuration could be, so there was about 8% of the incidents could be resolved by having a different JVM configuration. And of those 8%, 7%, so 7 out of 8, so about 90% of those ones would have been resolved by the garbage collector being in a different configuration, in a more optimal configuration. So that's not the cause of the incident, but that is a way that the incident could have been resolved if the garbage collector was more optimal. So it's quite an important thing to monitor. And then JVM operating system statistics, very useful to have because quite a lot of the time it's resources being exhausted on the operating system. So it's really useful to have those available. So that was a quick whistle-top tour of the JVM level ones, but there's also application level. And the main things you want to do is the latency. You want to measure the latency of your requests. You want to measure how many of your requests, how many there are and how many of them were successful and how many of them caused an error. And the error count is possibly the most important of these. I mean, people want the latencies, but in fact, if there's a problem, the error count gives you a very quick way of knowing that there is a problem. When we have an incident, we tend to see the very first indication are error counts somewhere in the system increasing. And so that's pretty useful mechanism to get an early alert that there is a problem somewhere in your system. A couple of other things that are very useful to expose in your metrics. Things that people who use a standard, almost every application uses a thread pool somewhere there. You should expose the metrics for your thread pool. That's really useful when you're tracking into the application, into the JVM, to see where in your application there's a problem. Quite often it is some kind of a thread pool issue and you're either underutilizing or overutilizing your thread pool. And it's really useful if you have the statistics and the metrics out there that you can just look at them and see that very quickly that they've been under or overutilized. And the last thing here is a circuit breaker. If you don't know what a circuit breaker is, look it up. You should have one your application should be using a circuit breaker. There's several frameworks that will allow you to just plug it in, and if you are using a circuit breaker, or when you're using a circuit breaker, then you should be exposing the metrics so you can see when the circuit breaker kicked in and how it was kicked in, how it kicked in. And those are really useful for troubleshooting. And then I'm going to look at the JVM configurations. JVM configurations. The first thing is load distribution. So if you're putting your application out in the cloud and you're using any cloud provider, or you're using Kubernetes on the cloud, or a cloud provider providing Kubernetes, whichever of them, you'll get a load balancer in the mix in there somewhere, and it seems like it comes for free. And you think, okay, I've got a load balancer, I don't have to worry about load distribution. It takes care of it for me. It's going to send out all the requests to all the different instances, and that's fine. That's my scaling taken care of. But it isn't fine. So this picture here, it doesn't matter about the details. If you can look at the distribution there, the colors in the top one versus the bottom one. If you look at the bottom one first, you can see that all of these lines are very closely matched. They all sort of go in rhythm together. There's some variation, but that's fine. And the top one, all the colors are very different. So what you're looking at are the requests being sent to multiple instances in a cluster. And the bottom one, obviously, the requests are evenly distributed across all the instances. And the top one, they're very unevenly distributed. And the top one is what you'll get by default, because the load balancers don't really balance very well. There's a number of different ways in which they fail to balance. And a lot of these are from sticky connections. We use keep alive requests as standard, and you should be using keep alive requests. I'm not saying don't use them, but they do need to be cycled. So if you're using a layer 7 load balancer, and that means that it's something that understands HTTP or HTTPS, for example, Nginx or an Istio proxy, or the application load balancer, the enterprise load balancer in AWS, then that's fine. Then they will automatically terminate the requests correctly and balance them across your instances. But if you're using a layer 4 load balancer, which is at the network level, then it doesn't know about the individual requests. It only knows about the connections. So it will set up a connection to an instance, and then that's all it will do. And it will balance the connections across the instances, but it won't balance the requests within the connections. And that tends to be where the unbalanced loads comes from. So if you have that situation, then what you need to do is cycle the persistent connections. And the way you do that is there's any server-side mechanism will have a mechanism to cycle through connections. For example, Tomcat has max keep alive requests, and each of the other ones, whichever one you're using, will have a mechanism to time out the length of time that a persistent connection lasts for. So you want to time that out so that they continue to be cycled. Otherwise, you get this imbalance. And what happens with the imbalance is that you've got 5 instances. Just going back to that picture, you've got 5 instances, and one or two of them are getting a lot more requests than the other, and the latency of those requests as a consequence will slow down because those instances are overloaded. And adding more instances makes no difference at all because the imbalance stays there. So you can't scale your instances like that. And what's worse is that sometimes the imbalance causes the overloaded instances to crash. And you think, well, that's fine. They'll get spread to other instances. But then you've got a whole load of requests slamming onto some other instances, and you can get this effect of a cascaded failure where the imbalances just carry on breaking one instance after another. So it's an ugly situation. You want to avoid imbalances for all sorts of reasons. So first of all, you should be looking for that. And secondly, here's just very straightforward. Just make sure you recycle your persistent connections. And there's a similar thing on the DNS side. which is that the DNS by default in the JVM will cache forever. You want to make sure that you don't do that. And in this situation, it's a slightly different one, but similar to the last one. Here, for example, if you have a set of load balancers, then when your JVM starts up and you start getting requests, the DNS will find the IP address for the and the modern cloud infrastructure is very dynamic in terms of IP addresses. So you don't want to continue. Are not cached forever, and that's quite important. The JVM garbage collection, as I mentioned earlier with our review of incidents, it's quite important to get this right. Now, it's a full hour's talk, so I can't put that into this one, but I've already done that for you, so that's great. In fact, it was this talk is the talk I gave last year at Java 2 Days, and so if you just look for garbage collection tuning or my name in Java 2 Days, this video will come up. It's the recorded one. It's been put on YouTube, and it's a very detailed and very straightforward mechanism for optimizing your garbage collection in the JVM. Anyone can use the mechanism that I've put together in there. So just go ahead and find that one for the garbage collection. Okay, so and then the CPU resource allocation, CPU memory and the resource allocation. I'm going to delay talking about that until I get to the Kubernetes section, because in Kubernetes it's kind of linked to the JVM resource allocation. You need to think about the two of them together. So I'll cover that in the Kubernetes section. So that was JVM metrics and JVM configurations. Again, can't be exhaustive in an hour, but these are the most important things that we've learned as we moved into the cloud. And now I'm going to talk about NoSQL and DynamoDB and Cassandra and DynamoDB and Cassandra. Moving to that, everything used to be relational and now it all seems to be NoSQL. And there's actually a very good reason for this. So this is a fundamental computer science theorem. And it says that in a distributed system, you can only have two out of these three, which is consistency, availability, and partition tolerance. It's the CAP theorem. So partition tolerance is quite a mouthful, and it means that if there are network failures in a distributed system and it partitions your system, so that there's like a network failure between nodes in your system, your applications will still, your distributed system will still provide reads and writes correctly. And that's network failure is the last one, that partition tolerance. People understand consistency and availability, but partition tolerance is about network failure. So you've got those. If you can only have two, then you've got these three little intersections here: CA, CP, AP. And the CA section, that's where relational databases tend to be. So they have strict consistency, which means that when you do a transaction, it is guaranteed everything is going to see either the before state or the after state of that transaction. That's what strict consistency means. And in order to get strict consistency, you have to do, you have to have the system ensure that all the nodes see that that transaction before it's available to be seen by the customers, the clients of that application. And that means it takes time, because you have to ensure that all the nodes have that that transaction stored. It takes time to do that. And that's why CA is not ideal for a modern application, because of the time involved in having that consistency available, put everywhere through your system. And the CP side, the most common CP side would be a distributed cache. So for example, if you're using Memcache, that's on the CP side. And if you take Memcache as an example, which is probably the most popular distributed cache, the way it does that is it's storing any particular item in one node. So when you're getting your data item from your master and you're storing it in your distributed database in your Memcache, it puts that data item in one node, and then anytime you want to retrieve from the cache, it finds out which node it's in using the partitioned hash, and then it gets into that node, which means that if that node is unavailable for either the node's gone down or the network access to that node is not available, you don't have that data item available at all. You have to go and get it from the master sources. So remember, this is a cache. So a cache means that it can have items deleted from the cache, not available from a cache. That's perfectly reasonable for a cache. But that's not really ideal for your customers. That it then takes a long time for you to then go back to the original source of that data item and go and get it. So this is the reason why the AP box at the bottom, or semicircle or intersection rather, at the bottom has become kind of the industry standard, and this is where Cassandra, DynamoDB, and a lot of the other NoSQL data, not all of them, but a lot of them land in there. And this is because this means that it's available, it's quickly available, and it's available even in the kids' situation of network failures, which happen all the time in the internet. So that's why these have become very popular. So there's a trade-off there. They're just right for most of the data that you present to your users. They're not right for something that needs strict consistency, like a payment. So for the payment ones, you want to fail over to, or not fail over, but you want to use the CA side or even the CP side. But for everything else, you want to be in the AP. And that's the reason why our industry has tended to make massive use of Cassandra, DynamoDB, and similar distributed NoSQL stores. And it does mean that you haven't got consistency, so data can be slightly out of date. So if you're using one of these, Cassandra or DynamoDB, the most important thing to get right are the data models, because most of the issues that we saw and most of the issues that tend to be seen come because the data model is inappropriate for your data. So creating a good schema, that's important. And it's actually straightforward. You just have to know that there's this mechanism available to do that. And really it's about, so I'm not going to go into this in heavy detail, but really it's about understanding that you start with your queries. So the queries that you're going to make, think about those first. That's the very first thing. So you think about what queries I'm going to make to get the data for my application. And every time you build a query, that is a different table pretty much in a NoSQL database. So the read queries are where you start with, not the write ones, but the read queries. Writes are updates. The read queries are where you start with, and you define the ones that you're going to make. And this should immediately say to you, hang on, what if I want to change the query later on and do a different one? That's one of the disadvantages of these NoSQL solutions. They're not very good for ad hoc querying. Okay, relational databases, fabulous for ad hoc querying. If you want to just do any kind of random query, these are not ideal for that. They're inefficient for that. You can do them, but they're not efficient for that. They're optimized for particular tables, for particular read patterns of access. So you want to think about those because that defines how your schema, your data model is going to be created. And if you were taught normalized form or third normal form or anything at university when talking about relational databases, all of that gets thrown out the window for NoSQL databases, data stores. You don't want to normalize data. You want to do the actual opposite. You want to replicate data. They are more efficient when you duplicate data to make your queries optimal. And there's a lot of support within Cassandra, DynamoDB for replicated data. In Cassandra, they're called materialized views. In DynamoDB, they're global secondary indexes. And they specifically support replicated data because that's quite an important way of optimizing the performance of these kinds of data stores. So there's a step-by-step. You come up with your queries that defines the columns, that defines the primary key, it defines the partition keys, and then there's a few other things, a few other steps that are secondary. So up to 6 is defining your data model. The rest is about how you're optimizing your use of the data model in Cassandra. I think I'm not going to go into this. I don't know how many of you are using Cassandra rather than DynamoDB, but it's all very straightforward. What my team put together a set of articles on doing this in DynamoDB, and if you look up Expedia, and if you look up slides immediately, then you can just search for Expedia tech blog DynamoDB. You can see that we put together a very comprehensive set of guides for doing this in DynamoDB and optimizing your DynamoDB system. There are some gotchas with DynamoDB. So one of the things is that scaling is not instance. And this is generally true, is that if you're talking about little, second duration spikes that last for seconds to minute to like 1 minute or 2 minutes, that doesn't work very well for, it doesn't work for Kubernetes either, as you'll see later. It doesn't work well for DynamoDB. Scaling in DynamoDB is talking about your overall pattern of access and not individual spikes. So scaling takes 10 to 15 minutes. You need to factor that into how you provision. One of the things is that the partition key is quite critical if you're doing any kind of investigation. You don't have access to knowing what any particular request partition key used unless you log that. So it's important. So it's important to log that, which you can enable. Takes a little bit of effort, but it's quite good. It works very nicely. You should TTL, time to live, all the data. Every time you update your system, you set the time to live for that data update. And you still want it in there, then what we do is change how that's done so that you have any recent data or hot data that you want to access, put it into newer tables and leave the old ones. So for example, if you're storing any time-specific data, just create a new table every month or every week or whatever, put the data into there and have the old ones available for reading if you want. So this is important also for I/O, and I'll explain in a minute why. But you can also archive old data and then access it in a separate way. And there is a 400 kilobyte item size limit. There's lots of workarounds for it. So the way DynamoDB scales, is that it partitions the system, and it does that behind the scenes, so you don't have to do anything yourself. So if you start off with, say, one partition because you've got a certain amount of data, a certain amount of I/O, then what happens is as the I/O increases and increases, it partitions the data across multiple nodes. And it does that all behind the scenes. You don't see this. And that's the way it manages, it scales up the IO so that it can distribute the IO requests across multiple different nodes. Wonderful. Well, that sounds brilliant. That's fine for scaling up. But then when you scale down, it doesn't unpartition that data. And what happens is that the IO provisioned is separated out across the nodes. So this is the same thing as, this is why you don't want to have hot and cold data in the same system, because if you had all your hot data, all the new, say the new data is the hot data and it's coming in all the time, then it's going to end up in one partition because it's writing to the new thing. Depending on how you've set up to partition. And what can happen is that all the old nodes, all the data with all the old nodes can have equal amounts of IO provisioned to the new one, but they're not used, and the new one is, and so it gets throttled because it doesn't have enough IO. So it's quite detailed. You need to understand about DynamoDB IO and how it partitions, but it's important if you're going to be scaling up and down that you know about this. Otherwise, you can end up with your requests being throttled, even though it looks like you have enough IO provisioned. Okay, so yeah, I'm good for time. We're going into the Kubernetes resources now. So the main thing you need to know about resource allocation in Kubernetes is there's two different parts to it. There's requests and there's limits. When you specify the resource available for a pod, you specify the requests, and that is what the pod will have guaranteed to it. And you can specify a different limit. And if that is different, the limit says the resource above which the pod will not get, if you like. And CPU and memory are treated differently. So CPU is actually time sliced on the system, and you cannot get more than the limit. It will never allocate more CPU than your limit to your pod. Memory is different. There is no way for the operating system to guarantee to time slice memory. If your pod requests more than your limit, it can do. And what happens is that there's a background process which is called the OOM killer, and if it sees your pod going above your limit, it will kill it. It will kill it on the same system, or in this, it'll kill the container and it'll restart the container within the pod. Typically, that's what will happen. So let me go through a specific example here. If your limit is 2 gigabytes for your pod, and your JVM requests more than that, the container will kill, the JVM will get killed and restarted. If your limit is 4 cores, then your JVM just simply never gets allocated more than 4 cores. Okay, so that's the thing about limits. And if you go back down to the requests here, if your request is 2 cores, then your JVM is guaranteed to have those 2 cores available to it. The limit is not guaranteed. So if your request is 2 cores and your limit is 4 cores, then you're guaranteed to have 2 cores available. And if the host system has extra capacity on the CPU because some others processes are not using what they've requested, then it can allocate the other 2 cores, up to 2 more cores to your JVM. And similarly, the request, you're guaranteed the 1 gigabyte. You might not be able to get any more than 1 gigabyte if your request is 1 gigabyte and your limit is 2. You might not get that. You might get it if that's available on the host. But then if you go above 2 gigabytes, your JVM is killed. So it's important to understand requests and limits and the difference between CPU and memory that you can get. Breaks that out into a number of different categorizations. So if you have request and limit the same value, and they're both non-zero, then that's a guaranteed pod. And guaranteed means that it has the highest priority. So when there's pressure on the node, what Kubernetes does is it can kill off pods, evict them, and then start them on a different node. And if you're guaranteed, then you're the least likely, your pod is the least likely to be evicted from the node. If any of the containers in your pod has at least one request that's non-zero, then it's called burstable. And in that situation, it's the next highest priority. And then if you don't have any requests, if everything is set to zero, no requests, no limits in there, it's a best effort pod. And of course, that's the default. And that's the one that's the most likely to be evicted from the node. So your inclination would be to make your service burstable, because if you go back to this diagram, yeah, I want to guarantee the minimum resources to ensure that I have my pod can run. And I also want to, yeah, take advantage of any extra resources that might be on the host. And in fact, that's the ideal situation for an individual pod. And it's the worst situation for a system, because if every pod is burstable, then they're all competing for resources, because they're all trying to get that extra space between requests and limits, and they're all competing with each other, which makes them all bad neighbors. So really, what you want to do on but much more often you have Kubernetes clusters which has a mix of applications. You want to, by default, make everything guaranteed, and only in the situation where you've analyzed and burstable becomes really useful, and you want to make that subset of applications burstable, so that you have a nicely performing system across all. Otherwise you end up having everything fighting each other for resources, and that's bad overall. So if you're looking at your individual application, then there's going to be a sweet spot. So there's going to be, obviously, too small, you're just going to choke your application. Too large, you're just throwing money away in terms of resources. If you're this is requesting resources. So there's going to be some nice sweet spot where you're not costing too much, but you're giving enough resources to your application to run very nicely. And the way to do that is to have an SLO, service level objective, which is a target, a set of targets for your application, those that you need to achieve. So it's usually a latency or a throughput target, or several latencies or several throughputs. And that's really important. So if you want to get the optimal use of resources, you need to have those targets. A quick note about CPU resources. The measurement of the JVM CPU is different depending on which version and which measurement mechanism you use. So whatever you're using, just validate it. Just do some experiments on your system on your test system to see that you think you're measuring the CPU, and the metrics you're reporting are the ones that you think you're reporting. And just a note at the bottom that internally the JVM rounds up the CPU, because in Kubernetes you can request fractional CPU. You can request 1.8 cores, but the JVM rounds that up for some things, not for everything, but for some things, to an integer number, because it needs to know, it needs to have an integer number for the number of GC threads and the number of threads in the Lambda thread pool. So just be aware of that. And there are some JVM thread settings. Adjusting your XMX and XMS sizes, you should first define the sizes and then define your requests and limits. And then one thing about throttling. So people see their pods being throttled and they think, oh dear, that means that we need to give it more resources. That's not the situation. Situation is, are you achieving your targets? If you're achieving your targets, it doesn't matter if the pod's being throttled. So throttling just means that your pod requested more CPU than the limit was available, so it just wasn't given more time slices, and that's not a problem if you're reaching your limit. So it's perfectly okay for you to have throttling. And the way to get optimal resources, have those targets, do performance tests. You can do it in production if you want, and then incrementally change how many CPUs, how many cores you allocate, how much memory you use, until you've reduced that enough, but you're still hitting your targets. And similarly, for resource configuration in the cluster, do a similar thing, but have aim to do a quick startup, because there are some types of hosts that you can allocate that have but it means that you can scale nicely. And I'm going to skip about cost allocation, and I'm going to go into Kubernetes scaling. We've just got time for this. So about overloading, that if you want to avoid overloading your system, first of all, you can try and get enough capacity. And the way to do that is that one in the middle, over provisioning or scaling the system. I'm going to talk about scaling, or you can queue requests if you have that capability in your application. And then at some point you're going to hit a limit, because nobody has enough money to scale forever. So at some point you're going to have insufficient capacity, and then you have to do traffic shedding, which is just basically dropping requests. And if you've ever connected to a service, to a website, and just have your request hang and the page never appeared, that's because it dropped your request. Or you can send back an error. So if another time you've gone to a page on the website and you've got an error page back, that's often a rate limiting mechanism. And back pressure is where your client, the client side, understands the rate limiting, it understands the error, and it reduces the number of requests it make per second in order to accept that it's overloading the system. Within Kubernetes, there's a bunch of different scalers. The cluster autoscaler here is this one. This is about increasing the number of nodes in the system. The vertical pod autoscaler is not very mature, not very used that much. The main system that you want to know about is the HPA, the horizontal pod autoscaler, which is increasing the number of pods in your system. And the thing you need to know about this one is that it's not instantaneous, okay? It has requests coming in, and here at the bottom one, here at the top one, if you look at that, say the requests are increasing over some period, there'll be a threshold period, there'll be a it takes a little period because there's a measurement, a sequence of measurements that have to happen. It takes a little while before the pod kicks in. That's this between the blue and the brown line. And then from the brown to the green line, that's how long your pod takes to initialize. And that'll be up to your application and pod startup time. So there's a little while before your pod can start taking requests. And you have to be aware of that. And you can decrease this threshold, but that makes it more expensive because it will start earlier and it might not need to start at all. And then you might have too many pods running. And similarly, you have here the traffic drops off, the pod will hang around for a while because Kubernetes doesn't just quickly terminate the pod immediately. It goes below the threshold. It hangs around in case that was a dip and the traffic's going up again. So you just need to be aware of this kind of delayed hysteresis action where the pod takes a little time to start up after you pass your threshold, and it'll take a little time to terminate after it's past the threshold. You need to be aware of that when you're talking about autoscaling. So autoscaling isn't instant. It takes a little bit of time. It's about gradually changing traffic and not about bursts of traffic. Okay, so that's me done. I am going to see if there are any questions. And I can't see any questions in the chat. So I think I'm right at the limit of the session. And so that's perfect. And I will say thank you.
Okay. If you have any questions.